This video will explain method of centers, or also called method of inscribed hyperspheres. What this does is it moves you through the center of the space so that you will always have a feasible solution at each step. If you look at the first graph, you'll see that x1 and x2 are the axes. You have a linearized function, constraint 1 and constraint 2. The objective of method of centers is to draw the largest circle or hypersphere if it's in multiple dimensions, and you move there from a given start point, x0. So if you look at that hypersphere that's drawn right below it, we have x0 on the right-hand side. We're trying to move to the center of the hypersphere, so that's the largest circle, and here we have the function line, which is drawn in black. GI constraint equals 0, so that's again the linearized constraint, tangent to the circle. The one that's teal is also tangent to the circle, and then G sub k shows that you do not have to touch the circle. Your update relation in general is x equals x plus alpha s. For method of hyperspheres, we're going to assume that alpha equals 1. Now, if you look at the little triangle that's made from starting at x0, going to the center of the hypersphere, going to the function line that's tangent to the hypersphere, that's drawn here. So df is basically your radius. Then del f, it's shown in the positive direction pointing away, but if it's in the negative direction, then df becomes a multiple of minus del f. You have s, which is your search direction, the direction you want to go. And we're calling theta the angle between the search direction and df, your radius. So from law of cosines, we have minus del f dot s is the absolute value of del f at the start point times s times cosine minus 180, because again, we are looking at the other side. So given that we have del f, that means for cosine of 180 minus theta, that's the same as minus cosine theta. So we end up with minus the absolute value of del f at x0, the absolute value of s cosine theta. Solve this for s cosine theta, you get this equation. And we also know that df is s cosine theta, that's given in this little triangle. So df then boils down to equation A. That's df. That's this one here. Now let's look at how do you get dj. This is a little more complicated. What we have is let's look back up here. We have dj, we have our start point, we have the distance from the start point to the line tangent. So that ends up being this triangle right there, with s being the search direction that gets you to the center of your triangle. dj is broken up into dj1 and dj2 so that we have two right triangles. And at the bottom part of the triangle going down is minus del gj, because that is the tangent line to del gj. So from trig, you have formulas for dj1 and dj2, and you can add those together to get the total dj. We also know that del gs is similar to del fs, so that's given there. And when you combine all that, you end up with an equation B, if you put in all of the pieces that were discovered before. We need to get rid of this del g at x0. So if you assume a Taylor series, first order, you can approximate del g times the del x as minus gj at x0. So that ends up turning B into equation C. Now, what is your objective here? You want to draw the largest hypersphere. So that means you'll maximize R, and R should be less than or equal to df or dj, right? If it's larger than one of those, it means it no longer fits into space. So therefore, your statement should be the max of R such that df minus R is greater than or equal to 0, dj minus R is greater than or equal to 0, where df has to do with the function, dj is with the constraints, so therefore there's j equals 1 to m. In this case, s turn into your design variables, so that's really important to understand. In other words, for method of centers, your problem turns into the minimum of minus R, subject to, and here we're plugging in the equations for dj and df. We're listing dj first, so it's del gj at x naught dotted with s plus the absolute value of del gj of x naught times R is less than or equal to minus gj at x naught. J equals 1 to m. Now please note that absolute value means the square root of the sum of the squares. For del f at x naught dot s plus the absolute value of del f at x naught times R is less than or equal to 0. That's because there's no function value, but there could be constraint value because you may not be on the constraint. This is the method of centers.